A warm welcome to all those who have joined. Today's webinar topic is IoT and machine learning. I've put together a bunch of slides. I'm not sure how much I can cover today, but if required, we can have a continuation webinar sometime later. So why is this topic relevant today? As you know, as you might have already known, there are billions of devices that generate data that exist today. It could be sensors, temperature sensors, soil, water sensors. It could be, something like images, cameras capturing images and sending it to the cloud. It could be payment devices. So there are so many, like billions and billions of devices that exist today that generate data. So that is one reason why this topic is very relevant. And companies are making use of such data to improve their processes, to deliver to their customers what they need and things like that. The processing power of computers have also increased tremendously. With GPUs and TPUs and whatnot available today, the processing is not a bottleneck anymore. I mean, it may still take some time to do a machine learning algorithm, to execute a machine learning algorithm, but still you are getting results at a much faster pace. So a combination of those reasons is what has made this topic very relevant. So, the first thing that you look at is what kind of data are we talking about? What type of IoT data is being generated? According to this graphic, 62% is time series data. So time series data is data generated with respect to time. So as time progresses, you get different sets of data coming from that sensor. So things like temperature sensor, air quality sensor, soil water sensor, cameras. These are all giving you time series data. So that is why a majority of these sensors are time series data. And you can see static images and video also constitutes about 20%, and audio. And there are so many different types of data, because data is interesting, because that's what makes these models work. So that's why I just put this slide. Now, there is something that every person who is going to work in this area have to be cognizant about, which is data pre-processing, because data as such is not cannot be made use of straight away. There has to be some processing. The reason is that the distribution of the data could be a problem, because in this particular case I've got two slides. The first slide has got a different mean or average. Like you can see, the average is about 10 for the first slide, and for the second one the average is about 200. So the distribution of data, I mean, this could be a feature. Like, for example, let's say you're trying to build a model that predicts the the price of a particular house. So in that, the features could be like the number of bedrooms, or the actual the price and things like that. So the price, as you know, varies in the 100,000 500,000 range, right? Whereas if you look at the number of bedrooms and things like that, that will vary at a much smaller, like it would be like vary from 1 to maybe 6 or 7, right? So you can see that the average and the standard deviation of these two different features of the same model is widely different. So there has to be some kind of standardization. So you need to have a comparable distribution of these features. So data pre-processing is very important, so that you make the model perform well. They have to converge properly. When the model, after training, it has to converge. Otherwise, there is no point in the model being used for prediction. So this is a typical time series data. This is actually one taken from Uber, where Uber has, you can see on the y-axis it's the number of trips, and the time in days is the x-axis. So over time, over every day, they calculate the number of trips that they have done, and they have plotted this graph. And when you have time series data, typically what you do is you use the way you use that for training is by taking a slice of that time series and using one slice as the input, and then using that to predict the output. So you basically, this is if you have past data, what you do is you take some slices of that and you take a particular slice, say that this is the training input, and then the next, based on the training input, you're kind of predicting the output. So you are actually training the machine with these. This will constitute one sample, and imagine if you slide it slightly, maybe a day further, you get another sample, and again another day you get another sample. So like that you get several samples. So you can get thousands and thousands of samples by doing this time series sliding mechanism. And this sample is what you feed to a model that trains itself, that learns the patterns, so that given a new set of input data, maybe for today, it can probably predict what is going to be for tomorrow or for the next month for that matter. So IoT means, IoT devices generate data. So what is the protocol? What are the protocols that are very common? There is MQTT, there is AMQP, there is COAP. MQTT is the most popular, as you can see here, and AMQP is something that, I mean, these are all publish subscribe type of protocols, except the constrained application protocol, or the COAP. That is a client server type of protocol. It's used very rarely, but it's becoming popular. But as you can see, MQTT is the most popular IoT protocol, and it's very lightweight compared to HTTP. That's why people prefer that over HTTP. And of course, there is also other advantages of MQTT. So now let's get to some applications. Okay, how many of us have noticed, gallons of water being wasted from a, neighborhood pipe, and doing nothing about it? And today, what happens is people pick up the phone and call the water authority and say that, there is a pipe leakage, and they come and fix it. Now, is there a better way to do it? Definitely there is, basically using machine learning and IoT. So here what happens is, let's assume that you have a network of pipes, and let's say you have some kind of pressure sensor device that is attached to these pipes. So these pressure sensor devices are going to send you pressure information as a time series data. So you get pipes P1, P2, P3, and so on, and each one is sending you this information. So let's say it is being consumed and it is being processed by a machine learning algorithm, and you have a series of stacked. This is actually deep learning. So deep learning involves stacks of, in this particular case, it's like batch normalization, that is BN, then ReLU is the activation layer. So it's a combination of that. So you have these multiple layers, and finally you have the softmax classifier. Softmax is about, it's the best classification mechanism, where you have, let's say in this particular case, let's say you have 10 pipes. So out of that, the softmax will actually predict the probability of a leakage in each of these 10 pipes with the corresponding pipe ID. So P1, okay, there is a probability of 0.3. P2, there is a probability of 0.9. I'm sorry, the sum of it should add up to 1. So which means if you have 0.9, then you can have only 0.1 across all the other pipes. So the highest probability is the one that is the actual predicted value of the pipe or identifier where the leakage has occurred. So that this is one option. And there are also instances where instead of using the pressure sensors, people use the sound sensors, because water, when it flows through normally, makes a certain sound. When it is when there is leakage and when there is pressure reduction and things like that, then the sound varies. So there is also a study that has been deployed in Paris, where people use sound sensors to detect the pressure variations, and thereby use that time series data to predict the leakage. Let's look at transportation. Traffic loops are very common today. Every minute, the number of passing vehicles is counted by more than 10,000 road sensors in the Netherlands area. And why is this useful? One of the application is vehicle re-identification. Now, vehicle re-identification is nothing but, let's say, somebody at the control system is searching for a yellow, Toyota Camry or something. Immediately, the data that is coming from all these cameras spread across the city, that is going to send these images of vehicles passing by. Now, one thing is it has to do a classification that tells you, okay, what color it is and what is the type of vehicle and things like that. So that information is there. Plus, in this particular case, the re-identification case, it's very similar to face recognition, where you have an actual image that is represented by A. You have a negative image and you have a positive image. So with this, you have something known as a triplet loss. So using this network, you can actually, you get a representation of the image in the form of a vector. And then you find the Euclidean distance between like vectors so that you know whether it's the same vehicle or not. So hundreds and thousands of images just flow by this particular algorithm, and then if you're looking for a particular type of vehicle, that will have a signature, that will have a particular representation, and the representation of the new images, if it is very close by, then you know for sure that it's the same vehicle. So that's the way in which it can determine, it can re-identify it's the same vehicle. So you catch that vehicle in one particular camera, the same image can be caught in another camera further downstream, and then be able to identify that it's the same vehicle. Surveillance. This is actually a security type of application where you can find the intrusion. Like in this particular case, you have got two rows of images. The first row of the image is the actual image, and you can see that the second row is actually a combination of the past and the future. So the first 5 samples actually the past, and the next 5 is actually the future. So it is actually predicting what is the future image. So you can see here t+1, t+2, all the way up to t+5. In the architecture above, you can see there's an encoder where you consume the image and then you encode it into some kind of internal representation, and then you have a past decoder which actually predicts the past image. So that is the past decoder, and then you have a future decoder. The future decoder actually predicts the future image. So you can see the future images are not predicted very accurately because but to some extent it is able to predict the future. Now the advantage here is that there is something called regularity scoring. So you calculate a regularity score for the future image, and the regularity score of a future image which is very normal is going to be different from when there is an intrusion. So in this particular case, you have an intrusion of a vehicle there, whereas I haven't put the video or the picture without the vehicle. So the picture without vehicle is a normal scenario. So the normal scenario will keep predicting, giving a regularity score which represents a normal situation. I mean, there may be people walking, but there is no that is a normal scenario. Now suddenly a vehicle appears, that is actually an intrusion. So that is the regularity scoring technique is what you use for surveillance applications. Agriculture, smart farming is becoming very popular these days. So you have 2,000 acres of land, and you have these drones that just circle around the land, and using thermal imaging, it can actually map the whole area with which are the areas that are devoid of water, which are the areas that require water, and which are the areas where there is an abundance of water in the soil. So based on that, you can control the pumps, whereby you don't have to water the entire land. You just have to water the land area that requires water, adequate water supply. So that is smart farming. Now, disease identification of plants. So this is something that we are planning to take up for the InApp 20 project. So you have the input image, and then you have what is known as a convolution process with multiple filters. So this is so through this mechanism, it is actually predicting one of 10 devices as the output class. You can see here 0 to 1 of 9. So there are 9 types of devices being predicted or classified by this neural network, and how it does it is through a bunch of filters. So you use a bunch of filters that does convolution. So convolution is a process of multiplication of a filter with the actual image in a first horizontal and then vertical, horizontal across and then vertical down, that fashion. So the filter moves across the original image in that fashion and then does matrix multiplication and comes out with outputs, and then finally you flatten out that particular output values into a fully connected hidden layer, and those feed into the softmax classifier that I mentioned earlier, and out of the 9 classes it would give the maximum value to the particular number or part of the vector that has the that has the particular device, a particular disease. So that's the disease identification. In the manufacturing sector, you have what is called predictive maintenance. So again, this is a time series data of the temperature, and you can see that this is actually for a press paper mill. So you have these rolls that presses the paper, and the temperature of that roll is indicative of maintenance. So you can see here the notification there, the alert says if the temperature is not lowered, the probability of the failure is 5% in the next 24 hours, 15% in the next week, and 40% in the next month. So that is the level of probability that this machine learning model, by processing the time series information that is coming out of the device, it is able to predict. So this is being used for doing maintenance, preventive maintenance in a predictive fashion. So even in the construction industry, you have machine learning and IoT being used extensively. So drones is one of the biggest application here, where the drones is nothing but taking pictures. Okay, so you have, it's actually a device. It's actually nothing but a camera, a moving camera that actually takes pictures of the construction site that is in progress. And you have robots, again connected with cameras. So these robots can travel anywhere within, and they would probably be controlled by some individual, some controller that would actually earmark the path that the robot is supposed to take, and then it goes and takes pictures. And what kind of pictures are these? I mean, these pictures can actually do this. It can detect abnormalities. Again, by sending these pictures, by processing them using a machine learning model, it can come out with things like, there is a tolerance error here. It can pinpoint that particular block, saying that there is a particular error. It can predict delays. For example, if you are expected, you are like 50% into the project, you are expecting an electrical conduit to be available there, to be installed there, and if it's missing, then obviously that is a overdue delay. So that type of indications it can give. So it's all about images, and then processing these images, time series data of images, frames of images coming out of these cameras, and then using that to predict some things. So healthcare is again advanced disease prediction. So you can do, you can predict that a particular individual is going to have diabetes in the future based on a bunch of clinical data gathered from the hospital system, on from the IoT devices that are installed on the patient, from the patient's medical data, the EMR medical data. So all these are data sources that can actually contribute to the prediction of a particular disease. So I think that it was in a nutshell was my presentation. Like I didn't go much into detail on the technology side, for obvious reasons. So I think that is a separate webinar altogether, and I don't think 30 minutes is a good enough time for a in-depth technical analysis of some of these machine learning algorithms and problems. So I hope this was informative to you all. And today's contest question: which is the most common IoT protocol available today? So you can choose your answers from HTTP, AMQP, MQTT, and COAP. Thank you.